All right. So we've spent a lot of time talking about factoring, and then we sort of added on finding the zeros pretty peripherally there, because that's something we talked about in the past. But if this isn't obvious to you, then this would be a good refresh on how we use those factors to identify zeros. So ultimately, if you're looking at a linear factor is going to be connected to a rational zero, right? So if you look at our example here, we've got f of x equals x times 3, x plus 4, times x minus 2, times x plus 2, right? Each of these is a linear factor. So x, linear factor, 3x plus 4, linear factor, x minus 2, linear factor, and x plus 2, linear factor, okay? This represents a fourth degree function because we've got four linear terms or four linear factors being multiplied together, but we have them sort of in this factored form here, right? So there's a fourth degree polynomial, so we should expect four roots. And in this case, because we have four linear zeros, then all four of those roots are going to be rational roots. So right, numbers that don't have square roots, numbers that don't have imaginary numbers in them. Okay. So to identify what the zeros are, we take each of the linear terms and set them equal to 0 and solve. Now you'll likely be able to see the pattern here and not necessarily have to actually perform this, but we can take each of those factors. So x is equal to 0, right? That one's pretty obvious. 3x plus 4 is equal to 0. X minus 2 is equal to 0, and x plus 2 is equal to 0. Okay, so the x equals 0, straightforward. Otherwise, when we solve for x, for this one here, we would subtract 4 over and divide by 3, giving us an x value of negative 4/3. For this one, we would add 2 over, giving us an x value of 2. And for this one, we would subtract 2 over, giving us an x value of negative 2. So if you were asked to list the zeros, then the zeros are just these values. And if you take any of these values and plug them back into your function, they'll give you a function value of 0, indicating that these are zeros crossing, right, where a graph would physically cross the x-axis, otherwise known as roots when we're not necessarily talking about graphing. So 0, negative 4/3, 2, and negative 2. Okay. Now, on the other hand, if you are asked to find the zeros, you may end up with something that looks more like, let's see here, I don't know if I've got a good one. That's a good one. And remember that I'm giving these to you in factored form. So the assumption is that we've already done the factoring to end up in this factored form here. So they can't be factored anymore. X squared minus 5. Right? So now, if we look, we actually only have one linear term, right? Each linear term relating to a rational zero. And then we also have this quadratic term, or this quadratic factor, x squared minus 5. And presumably, if we've got a quadratic, that means that it didn't factor nicely, and so there's no rational roots or zeros associated with that. Right? So the only real rational root that we're going to have is going to come from the linear factor 5x minus 1, which would relate to the 0, 1/5. Okay? For this quadratic term here, okay, that one we can't find a rational root from, so we need to solve it using a way we can solve quadratics. So a lot of the times, if this is 3 terms, it's going to be the quadratic formula or completing the square, usually the quadratic formula, because that's kind of our go-to. In this case, because there's no middle term, we could actually solve this by looking at just using some algebra solving skills. So we would set it equal to 0, add the 5 over, which would leave us with x squared equals 5. And then if we square root both sides, that would leave us with x equals plus or minus 5, or probably plus or minus the square root of 5. So that would give us our other two zeros there, right? So to list out the zeros, they would be 1/5, and then positive square root of 5 and negative square root of 5. Right? And those are rational, irrational because they have a square root there. Another option, so one more example to look at here, would be if I had something that looked like 3x plus 1, 9x squared minus 3x plus 1, right? So again, there's only a single linear factor here, 3x plus 1, which will relate to the factor, or the 0, negative 1/3. But we've also got still this quadratic here, and that one can't be solved as simply as in the previous problem. This one we'd have to use the quadratic formula on, and we'll find our rational root. So I'll run through that real quick. We're not going to spend a whole lot of time on the quadratic formula, but just so we can see those roots. So negative b squared ac over 2. So we've got x equals 3 plus or minus the square root of 9 minus 36 over 18. We could do a little bit of simplifying here. Negative 27 over 18. And then this will be a little bit of a reminder, but whenever we've got square root of a negative number, we can pull that negative out as an imaginary number. So we are in fact seeing that this is not only irrational, but it's also imaginary. Square root of 27i over 18. And you could potentially do some more simplifying, but for the sake of keeping this a little bit shorter, that would be our other two zeros for this third degree function that's split up into the linear term as well as the remaining quadratic. So to list out the zeros again, we've got the negative 1/3, and then we've got the 2 from the quadratic, 3 plus the square root of 27i over 18, and 3 minus the square root of 27i over 18, right? And so the difference between an imaginary root, like the ones you see here, and an irrational root, like the ones we saw in the previous problem, the square root of 5 and the negative square root of 5, is that imaginary roots they don't visually show up on a graph, right? We don't see, there's not an imaginary axis on our Cartesian coordinate plane, so we don't see those crossing, whereas with these irrational roots, right, that's where we're going to see the graph crossing. So the square root of 5 is 2 point something, right? So the graph would be crossing at positive 2 point something and negative 2 point something. And so there is still a difference between those imaginary and irrational roots, but if we have those, they're going to manifest as those unfactored quadratic terms.